Okay, should be fine. Okay, let's start. So any question from last time you should probably have because I made a mistake last time. So yeah, so let's part which is quite confusing this precision on face estimation. Yeah, so we have a quadrant mark on this. And so what's the error? The error is this interpretation on this precision. I was saying this means that we are taking the first n bit of the output, and there will be the correct first n bit, but that's not quite correct. So what we are actually trying to do is we are taking the 4 T-bit output. Oh, sorry, I should not use this color. Okay. So yeah, this is a bit subtle. So we are taking the whole T-bit output as our output. So remember, okay, yeah, remember this picture. So we are on this smallest, we are on those grids, and we are taking a T-bit output. So we will have a T-bit output string. And what do we mean by having an n-bit precision? It means that our error is at most 2 to the minus n. Okay, so yeah, this is a little confusing because remember t is bigger than n. T is n plus p. So we are saying we have a TB number, but it has n-bit precision. We need to do this, otherwise when the error is at 0.5, it's very hard to get it correct. Okay, so yeah, so our output will going to be 0.b1, b2, bt, and then we are going to say it has n-bit precision, which has n smaller than t, and it means that this number and the actual number has at most 2 to the minus n error, and then that's how you get this thing. So the calculation is that what's the maximum number of error you can have. So we look back to this picture. So the maximum error you can get here is, so you can just count how many tick here, right? We are saying everything in this plus minus e is correct, but then you have this half tick here. So the maximum number of error you get here is e plus 1 tick, and h tick is 2 to the minus t. So the maximum error you get is e plus 1 times 2 to the minus t, and we want this to be 2 to the minus n, and that's how you get e equal to this, e equal to 2 to the t minus n minus 1. You just move things around. Okay, so that's what we mean by precision. And also the other thing about this is that so this is what you do when you want really low error, right? So this can give you arbitrarily small error as you increase those extra bits. But if you just want okay-ish error, actually face estimation is very good. So there is something you can prove that. So when you do the TP thing, actually if you take all T bits, they are very good. They are at least this about 40% probability you'll get the best possible T-bit approximation. So basically, you'll get the result as like your 5 round of 2 T-bits. Or OK， 用中文来讲的话，就是会是你4舍5入的结果。Okay， and that means the error is less than, this should be t here. So this should be, because we're looking really in different reference. That means the error is less than 2 to the t plus 1 over 1. Okay, so 0.1 times 2 to the minus t. And in this picture, so we are looking at this picture, and if we like look at this part, so if we look at this part closely, then this means that the closest tick, so this probability value, So if the peak is on the right hand side, then this is the highest. Otherwise, you might have something like this, then this will be highest. But anyway, and if you want to balance, it's exactly in the middle, where your delta equal to 1/2. Anyway, so the highest point will be more than 40%. Okay, so even if you take all t-bit, you have a very good probability to get a very good estimate. Okay, I guess depends on how you think it is good, but this is constant probability to get the whole t-bit correct. Okay, so any question on phase estimation? And okay, so some story here is so this is actually enough for us to do Shor's algorithm. So many textbooks just use this. I believe Shor's original paper also use this. So this is enough for proving Shor's algorithm work. You don't need to get this one very strong precision. Anyway, this require, well, obviously other calculation, which we will not cover here. Just to let you know that we also have this kind of result is also true. Okay. So if we don't have more question on phase estimation, let's actually go to Shor's algorithm. Okay. So before Shor's algorithm, let's talk a little more about number theory. So this is the problem that Shor's algorithm actually solves. Obviously, we know Shor's algorithm solves factoring, but it does not by reduce factoring to this order finding problem. So what's this order finding problem? Is that if we have two numbers, we think a little smaller number x and a very big number n, and n is not necessarily prime. But anyway, we have x and n, and x is smaller than n, and when x and n are co-prime, so here we have this GCD, means greatest common divisor, so 最大公因数. With they are co-prime, so GCD equal to 1. And so the order finding problem asks you to find this number r, which is order of x respect to n, which means that x to the r equal to 1 mod n. And okay, so this is not quite correct. So I should say smallest, because x to the n probably is correct. So I should say smallest r. Okay. So the idea is that if you keep multiplying x to itself and mod n, mod big N, then eventually you are going to come back to yourself. So it's like the sequence, that's why it's called order. And so I guess let's go to this example here. So let's say you have x equal to 3 and n equal to 7. Then, well, x to the first power is obviously 3. Then now we want to do arithmetic everything like mod n. Okay? Want everything mod n. So now we have x squared. Well, x squared equal to 9, and you mod 7, that equal to 2. Then x cubed will equal to this 2 times 3. Then you mod 7, then, well, it's 6, so mod 7 is still 6. Then we have x4 is going to be 6 times 3, so that's 18, and you mod 7, that becomes 4. Then 4 times 3, so we keep doing this, 4 times 3 equal to 12. Then mod 7 becomes 5. Then 5 times 3 equal to 15. Then mod 7, finally, that's 15 minus 14, that equal to 1. Okay? And yeah, so you see the order here equal to 6 because that's the smallest number of power to the x that will equal to 1 mod n. And then if you keep multiplying 3 on this, you see this goes back, right? Because 1 times 3 equal to 3. So if you keep multiplying 3 and then take mod n, then the numbers are going to keep repeating, keep walking through those 6 numbers. So it's like a circle, and the total number is called order. Just going in this way. Yeah. And well, obviously this is the maximum possible because n equals 7, the maximum possible order is 7 minus 1 equals 6 because you cannot have mod 7 equal to 0. But you can have smaller order. So for example, if you start from here, right? So if x equal to 2, and you still take the bigger n equal to 7, then the order is going to be 3 because 2 is here, then 2 squared is going to become, I'm a little confused. Oh, okay. Yeah, so 2 is here, then 2 squared is going to become here, then 2 cubed is going to become here, right? So 2 and 4 and 8 mod 7 equal to 1. And so you see that the order of 2 is going to equal to 3. So this is going to be different number for different x. And the question, so this is another trivial problem. And yeah, so this order finding problem is asking you given arbitrary x and n, how can you find the order of x with respect to n? Okay, everyone got the order finding problem? So we already see that we're fixing n equal to 7 here, then for different x equals 3 and x equal 2, we have different order. Okay, so that's order finding problem. Then we are going to show that we have a quantum algorithm that do this first. Before we show the quantum algorithm, we need to define how big the problem is. So this problem obviously scale with x and n, and x is kind of arbitrary, but x is smaller. We are thinking x is anything else smaller than n. So this really is the dominating factor here is this big N. Okay? And so the scaling factor is how big N is. And because how you do, I guess it is a kind of convention. So instead of saying the scaling in terms of N, we want to say in terms of a number of bits of N. Okay, so how many bits or qubits do you need to write down n? So that's just the logarithm of n and take setting, and so that number we call it L. So we want to remember this. We are going to see L everywhere because it's a scaling factor of this problem, and we are going to count every constant in L. And anyway, L is this number of bits of n and is setting of log n, and it's our problem size. Okay, and finally back to 1 layer. So how fast can we solve order finding in classical or quantum algorithm? Classical algorithm, well, we don't exactly have an upper bound, but what we know is people try pretty hard, and we haven't found any poly-L algorithm. Any poly-L classical algorithm that can solve order finding. And well, we are going to see very soon that we have a quantum algorithm that use phase estimation and will do order finding in L cube. And I guess also let's show a little well, it's not quite approved, but let's show a little bit why we cannot do this. That is, we think about this algorithm, right? So if we just do the order finding by brute force multiplying x with itself, keep multiplying and until we hit the order. And because the order can be as big as n, then we see here that here, so the order can be, when we are unlucky, order can be like a -1, and then you need to do a -2 multiplication, so that it is order big N operation. And because big N, well, obviously big N is like 2 to L, so that will require exponential in L number of operation to find to find the order through this brute force classical algorithm. And yeah, so I'm not sure whether there are smarter algorithms, but that's the baseline you are looking at for doing a classical algorithm to do order finding. Okay, and but we are going to see that we have something very fast to do quantum, and this is really how the Schwartz algorithm can achieve exponential speed up over classical algorithms. Okay, and so but that's order finding. Obviously, what we actually want is factoring, and we'll probably have time today, and we'll show that maybe today. Anyway, so you can reduce factoring to order finding, and this is actually nothing quantum at all. This is some number theory. Okay, then let's see the quantum algorithm part. Okay, so how do we use phase estimation to solve order finding? What we do is we consider this operation, which is a unitary gate, if you think hard enough. And this operation is multiplication by x. I should say multiplication by x. Okay. And yeah, it's by x and mod n. Okay. And well, this is a pretty classical operation, and obviously we can extend it to quantum. So on computational basis, it does exactly what we say. You do multiplication by x mod n. So if you put in a computational basis state y, then it becomes a computational basis state xy mod n. Okay? And because this y and this xy are all going to get mod n, so you see this is a big N dimensional space, and this is big N dimensional space. So U is really a big N by big N matrix, and it's a big N by big N permutation matrix, and we are not going to show, but it's pretty easy to convince yourself that U is a unitary matrix, so it makes sense. I guess it being reversible means it's unitary, although we didn't quite prove that. And anyway, this is so this is the definition of U as a whole matrix, right? Because we define how it acts on all the computational basis state, and then you can do linear extension to define how it works on every other quantum state. Okay? Question? So this is a very classical gate. You just do multiplication, and in this Fn field, I guess it's not field, but do multiplication mod n. Okay. And as we said, everything is mod n. So this xy is something from 0 to n minus 1. And so basically what we are going to do is we are going to do phase estimation on this u of x. So what are the eigenvalue and the eigenvector of u of x? We think about this. I guess let's first think about what are the eigenstate of u of x. So there is something very trivial. This 0, because everything times 0 is still 0. So 0 has eigenvalue 1. Okay, but that's not very useful because we want to find the period of x. So how do we find the period of x using this ux? We probably want to start our thing with this x computational basis state. Well, if you apply ux on x, obviously it becomes x squared modern, because that's what ux do. It times x with x. So, well, x and x squared probably are different, so x is not an eigenstate. And if we keep applying ux on this, so if we apply ux on x squared, then it will be on x cubed, etc. And we notice that, so we keep doing this, then at some point we'll hit x to r equal to 1, right? And so if we keep hitting ux on x, then it will be very similar to what happened here, right? So it will just be cycling through those x to some power computational basis. And then we can use quantum superposition to create eigenvector here. That is, what if we just add all of them together in equal weight? Okay. So if we think about this quantum state, which we call small u sub 0, that is x, the computational state x, then computational basis state x squared, and plus x cubed all the way to x to its order r, which remember when we take everything modern, and this is really equal to 1 modern. And this should be eigenvector of u, because u just cycles through them, right? So you apply u on this thing, then x becomes x squared becomes x cubed, and x cubed becomes x fourth. And this x to the r, which is equal to 1, becomes x. And but you see this state is the same as this state because, well, obviously the ordering of summation doesn't matter. So your x squared goes to here, and your x cubed goes here, and you see your x goes to here. You are just shuffling things around. So yeah. So this u naught is eigenstate of ux. And what's the eigenvalue? Eigenvalue is 1. Because you apply u on u naught, sorry, you apply ux on u naught, then it's still u naught. So that's not too useful. Okay, so some digression. We are writing tilde here because we are being lazy. Because this is not a normalized state. Everything we think as a unit vector, so we should have 1 with square root r, but we are being lazy, so we just write tilde. Okay, so it means we are omitting the normalization. And anyway, so this is the eigenvector, and we can construct similar eigenvector in this space. So I guess a bit of counting. So there really are vectors here, right? So if we think about the space spanned by x squared all the way to x to the r, right? So if you think about this subspace, then so a bit of group theory, we think this subspace is really invariant under ux, right? Because anything in this subspace you apply u, you should still get a vector in this subspace. And so any eigenvector in this subspace should stay in this subspace. And this subspace, well, there are vectors here, and obviously it has dimension r. So there should really be r eigenvectors in this subspace, and we only find one of them. So how do we construct other -1 eigenvectors? We can do that by adding this phase. Okay. So this is very similar to Fourier transform. And you can see the Fourier transform, phase estimation, and everything. This is related. Anyway, so now we define this phase vector omega, which is the rth root of 1. So it's e to the 2 pi I, then divided by r. And for convenience, we also add the minus sign here. Okay. And okay, so this is a vector, and what do we do is, now we have a u1 equal to omega times x and omega squared times x squared over to omega to the r times x to the r. And you can see some symmetry here already. So x to the r, as we say, is really equal to 1. And omega to the r is also equal to 1. Okay? Although it's a little different. X to the r equal to 1 is like Adorner-Marden, and omega to the r equal to 1 is just because e to the 2 pi equal to 1. But anyway, so what happens when we apply ux on this u1 state, where we still have this x plus x squared to x to the r, but everything is multiplying some power of omega. And using this still get shifted around, right? So x becomes x squared becomes x cubed, etc. And x to the r become x. But so things still get shifted around, but now you see those omega doesn't match, right? You are losing a factor of omega here. Right? Everything is losing a factor of omega. And that's possible because omega is a complex vector. So that means that this omega to the rx, actually omega to the r, as we say, equal to 1. And that is omega times omega minus 1. So what I'm trying to say? What I'm trying to say is ux u1 equal to omega minus 1 times u1. And that's kind of, we want a negative sign, because this is equal to e to the r2 pi I u1 with a plus sign here. Okay. Okay. Everyone getting this? I think this is the most important thing for today. You need to know how phase estimation. No, this is not phase estimation yet, but you need to know why this is true. Then you know how this helps us do order finding. Okay. Everyone clear? So you see U1. Okay, then you are good with this. Then now we see this U1 is very useful now, because if we do phase estimation with U1, then we are going to learn this 2 pi over r. Okay? And well, 2 pi over r is r over r here. Okay. Yeah. And so if we can get a hold of U1 and we do phase estimation, then we know r, then we win. Right? Very cool. Remember, this is what the order trying to find this r. Okay. So that's a bit ahead of ourselves, but that's the essence of what order finding trying to do. Obviously, there are a lot of detail to make this simple idea actually work. So let's back to our eigenstate counting. We said there are going to be r-1 extra state, and only find one of them. And well, it's not too hard to find other eigenstate. You just replace this. So kind of like the Fourier transform. thing. So you just replace this omega with omega square, omega cube, etc. As you replace this omega, then you will have omega force here, etc. And okay, so I'm too lazy to list them down. But if you write those in algebraic, then you can define this U sub S, where you have S equal to 1 here, and this S is just the power of omega you put here. And so now we have a very formal definition. We can define this U sub S, which is going to be an eigenstate of Ux, and equal to 1 over square root r, 1 over square root r for normalization, as I mentioned. K from 0 to r minus 1. So k from 0 is actually here, then k equal to 1 here, k equal to 2 here, etc. Then we have this, so we are writing all omega. So exponential minus 2 pi I divided by r, then s times k, right? So basically e to the 2 pi I divided by r is omega, then omega to the s power. So here we have s equal to 1, but s can actually also equal to 2, 3, 4, 5, and all the way to r, which equal to 0. So we can also have s equal to 0. So you see that we are consistent with our notation. If s equal to 0, then these factors are all equal to 0, then we just exponential 0 equal to 1, so we have a whole bunch of 1 here. So we have a u0 here, u1 here, and then you can actually also have a u2, 3, 4, 5 all the way to r minus 1. And yeah, so that's a factor exponential e to the 2 pi s, and to the k's power, you can see this keep on multiplying. And at the end, you have this computational basis x to the k. So x to the k, so this counting is a little different. We count from k equals 0. So k equals 0 is this x to the r, because everything is cycling back in order. So k equals 0, k equals 1, k equals 2, etc. Okay? And yeah, so I forgot to say here, but obviously we have, let's use red so I remember. S is from 0, 1 to r minus 1. Okay? So this is where we get our different eigenstate. Okay? So we have our eigenstate here with this from, so u0, u1, all the way to u r minus 1. Okay? And we see, well, u0 is kind of useless because when you learn its eigenvalue is just tell you eigenvalue is 1. But for every other s, its face is going to tell you something about r, because so you can check out the math. So, but if you apply ux on this thing, then similar thing will happen. Things similar to this will happen, and you'll see that the eigenvalue of us is this omega. This is omega to the s, which you write down. Then it's exponential e to omega to the minus s. Okay. So this is exponential e to the 2 pi over r s. Okay. And if we ignore this 2 pi r, it's kind of constant. Then from here you can learn r divided by s. Okay. Divided by r. We already said. Sorry. Yeah. So if we get hold of some us, and then we can run phase estimation of ux with this us, then we will learn s over r. And phase estimation of ux is possible, right? Because ux is just multiplication, although we didn't quite sure. But we can run any quantum superposition of classical operation on a quantum computer. Okay. I guess a very short proof, 5-second proof, is that remember we can do Toffoli gate. Okay. And Toffoli gate is universal for classical computation. So it's possible to do every classical computation on quantum computer. Okay. But anyway, hope you believe that this is possible. But there are some more issues here, as we will see. Anyway, back to here. So we want to run phase estimation of UX on US. But now we have trouble because how do we actually get a copy of US? You see, this is pretty hard. Seems pretty hard to get any copy of US, right? Because these things seems very dependent. If you want to brute force create this, then things like you need to know R to. You already need to know R to create this thing because you want to know every of those. And you want to know what's omega, so you can pay the phase here. But the problem is already you don't know R, so how do you create this? And the answer is you don't. Okay? We cannot create any of the US. Okay, that's pretty hard. Probably requiring you to know R. But you can create a superposition of every US, and that's just a computational basis state 1, which also equal to x to the R. Okay, remember 1 equal to x to the R model. Okay, and that's a Fourier cancellation again, because you can check that if you add all of them together. So you add, okay, so I should really say here. Okay. So if you add all of those US, so it's from 0 to R minus 1, then that will equal to that will equal to 1. So everything except this x to R will get cancelled. And you can kind of see that is true for the Fourier cancellation, right? Because the coefficient in front of x to the R is always going to be 1. So it's not going to get cancelled. Right? You can also read here. So if k equal to k equal to R, which equal to k equal to 0, then the phase here is 0. So it's always going to be 0. And if the coefficient is, if k is not 0, then you are going to sum over those exponential. And that's a Fourier cancellation we keep saying. Let's see if we can go here. Yeah, it's this equation once again. So let's write this one down once again. So cos 0 equal to summation to 1 to j, maybe let's change to, what do we have here? K. No, S3. 0 equal to summation S0 to minus 1 e to the 2 pi I sk over R. That's also A minus. If k not equal to 0, so this is equal to this. We're just changing worldwide in negative sign, but that's doing complex conjugation, and complex conjugation of 0 is still 0. And so J become S and R become N, and K is still OK. Okay. So this is exactly because of the Fourier cancellation I talked about. And if we want to check once again, let's see more examples. So let's say the first, when k equal to 1, then we'll have u0. This x component has amplitude of 1, and on u1 U1 is here. U1, the component have amplitude of omega, and obviously on U2 we didn't write down, but on U2 it will have excuse me. On U2 you will have amplitude of omega 2. So when we add all the way through, then we have 1 plus omega squared plus plus omega to the r minus 1, and that will equal to 0. Okay? Everyone okay with this cancellation? Let's erase this. Okay, so yeah, so that's why 1 equal to this equal superposition of every US. And then how do we use this fact? We use this fact by doing, so we don't do phase estimation on US, we do phase estimation on 1. Then that goes back to something we talked about. Okay, so remember we have this thing. Okay, now it's hard to find here. Yeah, so that's why we talk about this. If we don't use actual eigenstate, and instead of using a superposition of eigenstate, then we say we'll get random phase result corresponding to that eigenstate with some probability, right? Excuse me. Yep. So this is exactly what happened, and the CU here is going to be uniformly distributed. So the CU here is going to be this 1 square that. Excuse me. And so basically we are going to pick a random US with uniform distribution, and that's run through once again. So if we have a register that for recording our phase estimation, and we have our phase estimation state running on 1. So let's do this here. Remember our phase estimation here. So we are thinking, so this 0 is actually 0 to a t. So maybe I should say 0 to a t. Okay, let's say 0 to a t. And this 1 now is n-dimensional 1. So that 1 is this U register. And then we run phase estimation. Then because 1 is not actually eigenstate of U, so then we decompose 1 equal to eigenstates of U, and we know 1 is the summation of different US with coefficient 1 over square root r, and its phase is going to be this S over R, because we just proved here. Phase is whatever things multiplying these 2 pi. So we are going to get S over R here, or like 2 to the t times S over R. But let's ignore the 2 to the t here for now. And then if we measure the first register, we are going to get this S over R, and each of them. So there are different S. There are different S. As we said, and each of them is going to be picked with probability 1 over R, the uniform randomness. Okay. And what's going to happen is we are going to draw a few of those S over R, because some of them are bad for many reasons. As you can see, let's say if we draw S equals 0, then that doesn't tell us anything, and it's really bad. And the other S has different reason for being bad, but we can repeat this, right? Because why not? So if we repeat this, we are going to get different S over R, and we're going to get S1 over R, S2 over R, and we are going to be able to calculate R here. So that's I guess that will finish the quantum part of Shor's algorithm. This using phase estimation on this multiplication unitary multiplication gate, and while treating 1 as your eigenvalue, as your eigenvector. Okay. So that's how you do order finding on a quantum computer really quick. I guess I can comment on, I don't really know what do you think about where do we get the quantum speed up? Seems like because we can do multiplication on all the we can do multiplication on all the R state simultaneously. People like to think about it. I don't think we have a very definite answer of why do we get a speed up here, but it's interesting to think about, and well, you see the math work out and it works. Okay. Yeah. So I guess one way to think about this is because it's quantum superposition, you can do this multiplication on all registers at once. But you can also think about this as this is because it is possible to do this phase estimation. So you can do this quantum Fourier transform really quick. You can do this quantum Fourier transform really quick, allow you to do phase estimation to extract this x over r.
Where's that 2 pi I?
It's just the definition of phase estimation. Because when we, let's see, can we, maybe here? Yeah. When we say we do phase estimation, we, let's see. We basically define it this way, right? If the phi is always a number between 0 and 1. So we are ignoring 2 pi. Okay, here. Right. When we define phase estimation, we already figured out the 2 pi. We say the phase is going to be 2 pi times some number 5 from 0 to 1. So we just omit the 2 pi. It will make things easier. Okay? Okay, I'm slow enough today. And 2 minutes, I can probably go through this. Okay, so that's the whole quantum idea of Shor's algorithm. Now we are going to get into a bit of a annoying part. So non-quantum parts. So there are a lot of non-quantum parts we do need to fix on this algorithm. So first thing we already kind of hint. So we need to apply this. Okay, that's why I have the here. So we need to apply this T-level control U very quickly. Okay. And well, we say our UX is multiplication. So obviously we can do multiplication things, just do it classical way. But that's not fast enough because you are going to do multiplication up to so T is going to be up to like big N, or big N, and we'll want to do things. So big N is like 2 to the L, and we don't want to do 2 to the L multiplication. That's way too much. Fortunately, there is way to do this, and that's why we write down this circuit, this repeated this U and U squared. So these powers of U circuit, and yeah, we are going to see that each of those separate block we can do very efficiently by doing repeated squaring. And it's time for a break, so let's have a break, and next class we are going to see what are the issues I can fix on Shor's algorithm or order finding. Okay. 作业，哦，
加页，
这个难怎样？算不出来吗？应该可以吧？
因为他最后一题是说需要几次的那个，那个问的是指那个是指问发一个题点，是指这个 case， 还是什么一般的 case？
对啊，就是只有假设它只有3位这样，我们说先知道它只有这样。
我只用了3个，
你只用了3个，可以这么强吗？我是没有，我记得要4、5个，可以这么快吗？
我想说，
你有这么厉害吗？应该不行吧？我记得至少4、5个吧。
可是 K 如果是4，那这样不是就会变成
A 等于4，啊对啊 ，A3 可以直接拿到嘛，对吧？
对，我有100%的机会可以拿到0或1。
这是可以的。然后接下来就拿什么？
根据0跟1，然后我可能换成sin或 cos，然后我还是可以。
有这么好吗？我记得没有。
这0可以想的就是这样。
为什么？我觉得应该不太可能吧。
然后00的话就是这样，10是。
可是应该有失败率吧？为什么你可以100%的做出来？我记得每步可能都是
算出来是92.5%。
有这么高？有这么高吗？我倒是没有很仔细算过，就是有可能。有这么好吗？应该没有吧。应该是从后面接回去吧。的确是想要这样做。
是 A3嘛，然后是 A。
没有，你是 A3，这应该是 A2，
A3好。
你 A3，所以应该是 A2。A2，对 A2为什么？
然后0.00是就是这个方向，然后10是。
就是你可能还要全部吧，就是 A3 是0的时候简单嘛 ，A3 是0的时候 ，A2 呢也是100%的，这个可以。但 A3 是1的时候，你这个后面有这个 A 后面挂0.1就嘛。
3就可以把这2分法。
哦，这么好。
那这个还是照算。
哦，对，就是等于是其中的。
我想看，它是4个东西。
而且如果这位是0的话，那其实就只有2位。
对 ，OK， 所以这边的确是3次，然后这边，然后再接下来，OK， 对，那接下来这里
可能就会出现这种
这里就真的要太难了吧？
什么45度的这种。
对啊，45度的不就是你至少要做个2、3次哦。
可是这样2分之根号2大概就有85%可以得到。
对，但我们是90%是不是？
对，那这样平均起来100%，然后跟85%。
不是 OK， 所以我没有讲清楚，但是那个几率应该要是 worst case， 就是对任何 case 都要90%。OK， 我们没有仔细讲这个，但是应该是要任何 case 都要90%的。
是任何 case。
对，不是什么 uniform distribution input， 通常是讲 worst case 的几率，所以这里至少还是要做过2次吧。所以应该是，现在看起来4次就可以。
这个方法就没办法 general 了，就因为几率只会越出越少。可是我不知道那个要怎么，因为我这个做法好像就没办法越来越精准，要怎么变成？
什么叫变精准？就这里就多重复几次就会变精准了。
你的实验就重复多做几次。
对啊，对啊，就是80%的确多做几次，这个就是可以用 turnover 的地方嘛。虽然说其实好像也不需要用 turnover，因为2、3次就结束了。所以我应该要弄个 epsilon 之类的，才可以让你们认真去算 turnover。
所以用 turnover 就是在这个85%下面到90%。
可能用 turnover 可能放的不怎么漂亮，就是说明直接算比较漂亮。你要弄个小一点的，用个什么1%的。对吧？
有时候我可能是什么15%拿到0，然后我再给它翻转一下，变85%拿到
0。可以啊，反正有3个口站可以试嘛。
对。
正确。好，时间哦，还够，去上厕所。 有问题吗？
那如果我们拿到考卷，
拿考卷，考卷应该在我的办公室。你有拿走吗？没有。考卷应该还在我办公室。如果你想的话，可以下课直接跟我上去拿。这应该是最快，不然的话，我可以看看明天或者下个礼拜记不记得之类的。
OK， 那我在写，因为我待会还有事，我在写信跟教授约好。
你是平常不会来上课吗？还是？
礼拜一会来上。
礼拜一会来，那我礼拜一试着拿过来，拿过来。然后如果没有，还是你会平常会拿作业回去吗？我也可以丢给主角，然后你就去主角那有一个盒子，然后你可以去拿之类的。
OK， 好，那我就在写信跟主角。
或者就
你们有那个
445，就是我办公室外面会有个抽屉，然后我等一下跟老师拿，我就把东西放在那边。
那就很方便，因为我在4.5楼。
OK，那
好，好，谢谢。
好。Okay. Okay. So let's get back. I guess let's still review this. So, quick review. So we are trying to do factoring, and we cannot to do factoring. All you need to do is solve this order finding problem. Where order, so we have two inputs to this problem. We have x and some big number n, and they are co-prime to each other. And we want to find the order of x with respect to this big number n, which is the smallest number r, where such that you keep multiplying x with itself, and it becomes 1 mod n. And we give this order finding algorithm that's really efficient on a quantum computer, and it's done by doing phase estimation. That's why we spend a lot of time talking about phase estimation. And it's phase estimation on this gate, which is multiplication by x mod n. Okay. You can see these are just multiplication by x mod n written all in algebra. And we want to phase estimation on this gate, and on the state 1. Okay. That's because 1 is the uniform superposition of this eigenstate of ux that are related to this x state. Because we see that if we put 1 or x inside on this, how should I say? If we feed x to this ux, they're going to give you x2, x3 all the way to x2r. So this is invariant subspace under this n-dimensional space. Sorry, invariant subspace under this ux subspace out of this n-dimensional space. And if we look at the eigenvectors of ux inside this subspace, you find out that there are those u's which are basically uniform superposition of x squared all the way to x to the r equal to 1, and but paired with different phase omega, where omega is this r root of 1 with a minus sign. And anyway, so u's are those states 1 over r exponential e to the minus 2 pi I over r is times to the k and x to the k. And the eigenvalue of us is going to be exponential 2 pi I and s over r. So when you do phase estimation on us, you will get s over r, but we don't know us, so we do phase estimation on 1, which is a uniform superposition of us. Okay, so we're kind of doing Fourier transform back and forth. and anyway, you do phase estimation on 1, then you get a uniformly random S over R. Okay. And so that's the idea. We are going to do this whole bunch of time, and we are going to create a whole bunch of fractions S1 over R1, S2 over R2, etc. And that will allow us to calculate R, and number theory is going to show us how that allows us to factor some number. Okay. And okay, so many tricky points. The first one is we need to implement phase estimation efficiently. In particular, this control stage u to the k part. So if you do this in a stupid way, then this requires about 2 to the t, which is about bigger operations here. And that's too slow, so that's why we'll actually use something like this, and show that repeat squaring allow you to do this very efficiently. And then the second problem is wait. Oh, okay. Sorry. So our estimation of S over R has error. Okay. Remember phase estimation, or let's say, phase estimation is error as we said. Phase estimation is exactly precise only if R is equal to 2 to the t, right? 2 to the some power. But if R is not some 2 to the some power, then the phase estimation is error. And then you need to correct that error. Well, we have the error analysis here, but just have a small error is not enough, because you really want this fraction here. Like when this is 1 over 3, then you really want 1 over 3. You don't want 1.0001 over 3.002, because that's very far off. You don't want your R to be 3, then if you like retain this inflection, then you see your R is 3002, but that's not true. Your R is actually 3. So you don't want something like this. So we'll get rid of that through continuing fraction. Okay. And the other problem still related to R is that the S you find might not be coprime with R. So extreme example is S equal to 0, as we said this class, right? S equal to 0. It's a kind of a singular example. But S equal to 0, then it's R over R equal to 0. Then you are just not getting any information. But the less extreme example is say R equal to 6 and S equal to 2. Then you run phase estimation. But phase estimation don't really know you are estimating 2 over 6 or 1 over 3. So you are just going to get 1 over 3. Okay. And okay. But you get 1 over 3, but your R is not 3, your R is actually 6. You are just drawing x equal to 2. So how do you do that? How do you deal with this is you are going to repeat your phase estimation many times, and you'll get different s, and eventually, and so how you solve this is really easy. Then you just do LCM, so largest common multiplier on all the R you get, then so yeah. So let's say you have one time, so you draw x equal to 2 here, then maybe next time you draw x equal to 3, and then you get 1 over 2, then you see this common multiplier of these 2 and 3 is your 6, and you are good. Okay. So okay, so that's the three things. It's all very classical technique. Any question? If not, then let's go through them one by one. So first is repeated squaring, or that's called modular exponential. So the idea is, well, if you just repeat squaring is some number, then you can calculate the exponential to some power very fast. So here we have an example. It's easier to see through this. So if you want to calculate some number to 17th power, and the dumbest way you do this is you have x times x times x, and you do multiplication. So then you write down these as a sequence of 17 numbers. Then you need to do 16 multiplications, just 17 minus 1. Right? And that's a lot of multiplication. But if you write your 17 in binary, so you think 17 is 16 times 1, but sorry, 16 plus 1, kind of like this. Then you can actually do this x to the 16 part really fast, because you can do x times x equal to x squared, and instead of x squared times x equal to x cubed, just do x squared times x squared equal to x fourth, and x fourth times x fourth equal to x8, x8 times x8 equal to x16. And so you only need to do 1, 2, 3, 4, 4 multiplication here. Then you times your x here, then you get your x17 with just 5 multiplications. Okay? So yeah, that's the idea. Repeat squaring. You do this kind of thing. Then you can do x to some high power really fast. So basically you can do each of those very fast. If you do each of those with repeated squaring, then you only need to, so you have like 2 to the t, then you only need about t multiplications to do this, right? Instead of 2 to the t multiplications. Okay. And but if we say this in more classical terms, this means that if we want to calculate some multiplication of x to the r, then we only need to do log r operation, because we write in binary, and then the length is r, and then the highest power you only need to do log of it. Okay, and then if you count everything carefully, then you see that back to here. In order to do this whole thing, then you need to do about order L cube operation to do this thing. Okay, here I'm just clearing it. We are not counting the detail, but you can see that's believable. I think it might be smaller, but anyway, it's going to be smaller than cube, because here we have like linear, and there are other things you can probably need, but it's going to be smaller than cube. Okay. So yeah, order L cube operation to do this part, and that's also the complexity of Shor's algorithm, order L cube. Okay. Question? No? Okay. So that's how we do this really fast. We do repeated squaring, and this is really kind of only possible because our unitary has a particular structure, right? So it's just something to take care of. So if your unitary is given more like a black box, where you don't have this repeat squaring structure to get this very quick, then doing phase estimation will be much slower, because you want to get this control u to the k, then you probably need to just do u to the k times. But here we have this structure that let you do repeat squaring, and it can be very fast. Okay, so the other thing we need to take care of is estimating S to S over R to actual group fraction. And that is done by doing this continued fraction algorithm. Okay. And okay. So let's state the problem here once again. So if your R is not the power of 2, then we'll have some error to our phase estimation. And let's say, so from the number we have on this next chapter, so we take our t equal to 12 plus 1, 12 plus 1, and this log 1 over epsilon terms. Then we will have 12 plus 1 bits over precision, although it's a little funny. But let's ignore that, because we will not do too detailed calculation here. We'll just show the idea. But anyway, so we have some precision, and there is some probability of error. And but now the question is, we get this side with some error, then how do we find this S over R with R not too small? And we see what this is a problem here once again. So let's say we phase estimation, and we get our psi equal to this in decimal 0.25001. And you see this is, if you look at the human eye, you see this is really close to 0.25. And I think your R is probably 4, or your S over R is probably 1 over 4. But how do you tell a computer to do this thing? And that's where we get continued fraction. And let's now write down the exact algorithm, because it's pretty easy to see this through an example. And so this is how the algorithm do. So you start with your phi equal to 0.25001, and well, you write it as something dividing something, right? So you write down this as S over R, so it's 25001, and divide by 1000000. Okay. And so if you don't do any error correcting things, then you are just going to say your R equal to this 100,000, which is very far away from 4. Now what you do is you write this thing, you flip this around. So you write this as 1 over 100,000 over 25001. Okay, so nothing really happened. Then you actually do the division here with some reminder. Okay, so this part. So you flip this around as 1 over something. Then because phi is less than 1, then now this is bigger than 1. So you can do this division with reminder, right? And you do a division, then you find this is 3 plus 24997 over 25001. Okay. And then you have this part. So you do the flip around once again. So this is 1 over 3 plus 1/2501/24997. Yeah. And now we'll do division once again. So you have 1/3 plus 1 over, then this into division, then you get a 1 plus 4/24997/4. Okay. And okay, now it's still sketchy, but you can imagine now this is something possible for computer to do. You see, this is a really small thing. So we just discard this. And if you actually want to run an algorithm, you will just say check whatever reminder you have, and if it's smaller than some threshold you set, then you stop. Okay. And anyway, so our threshold here, maybe let's say our threshold is 0.01, say maybe. Then we throw this away because it's more than 0.01. And then we see that our phi is about 1/3, and then we have 1/1. And so that's 1/4. Okay. So that's an example of how continuous fraction works. And we basically just claim that this works. Okay. So we don't have two regress of proof. Oh, sorry. Let's clean this up. But well, anyway, in general, we have continuous fraction of some number or equal to something like this form: a0 plus 1/a1 plus 1/a2 plus da da da. We probably don't have this a0 because our phi is less than 1. But anyway, we have a theorem here claiming that continuous fraction is pretty good. And the theorem, I think we'll have more proof of this theorem in our homework. And the theorem says that for S over R, okay, so the S over R is the thing we want to find. And if our phase estimation gives us this phi, and so phi and this actual fraction, if the difference is less than 1/2R squared, then we can find, and the point here is that this R and this R is the same thing. Then continuous fraction will find this S over R by cutting off at a good point. Okay. And so what do we say here? So here basically says that so this is a precision we need to have. Okay, this is a precision. Precision, which is the thing we spend a bit of time talking about, right? So we just need this 1/2R squared equal to our 2 to the minus n, or this or in terms of e, then it's e times 2 to the minus t. Okay. And let's see. Yeah. So that's how, and that's why we set our number here, right? So our 2 to the minus n. So so we want our 2 to the minus n to be smaller than this 1 over 2r squared, and our n is set as this 12 plus 1. Okay, and now you can see that we pick our number correct. So our 2 to the minus n is 2 to the minus 12 plus 1 is smaller than or equal to 1 over 2r squared. Okay, let's write this once again. 2 to the minus n. If in terms of what we have, this chapter is n. Okay, and I think we'll have a proof of this theorem in homework. So yeah, you can expect that. Question on the continuous fraction algorithm. I think it's not a total proof, but very close, something close to this thing. Just there are not too many fractions if you know this thing is true. Okay. Okay. Then if we don't have question, no, we are on good schedule. Then let's solve the other problem. So the problem of you are drawing uniform S, okay? And as we say, we are going to draw S as uniform. And here we actually change a little notation. So let's say the thing we draw is S prime. So we are going to draw our S1 prime, our S2 prime, etc. And then now the problem is this S1 prime and R might have some cofactors. So what we actually get is some S1 over R1 that might be different from S1 over R, and some S2 over R2 that might be different from S2 prime over R. And so we cannot we solve this by actually. Okay, so this is a bit funny, but it's easier to analyze. So only draw two of those. Okay. So we are going to draw S1 over R1 and S2 over R2, and then we take the least common multiplier of R1 over R2 against R. We get some least common multiplier, and this will be correct answer if only just use two of those. This will be correct answer with probability bigger than 1 over 4. And so we just keep doing this, and you'll get a correct answer at some point. Okay, and we can check the answer is correct very easy. Remember, we have repeated squaring. So whenever we see R, we can just calculate x to the R very efficiently and C is actually equal to 1 more than. Okay. But once again, so what's the general idea? The general idea is, let's say your R equals to 6. Then maybe you draw S1 prime equal to 3, S2 prime equal to 4. Then your S1 over R1 will be 3 over 6, but you are actually going to only see 1 over 2. And S2 prime over R, then what you are going to see is 2 over 3. And you see the 2 and 3 here, then take the least common multiplier, and you get a 6. Okay? So that's the idea. And so what's the probability that this kind of good thing actually happen? Or in other way to say this, what's the probability that something like this doesn't happen? So you need to be pretty unlucky. So we have a half proof here, because the last step is also in homework. But the idea is that if you want something unlucky here to happen, then you need to have a bad prime here. Okay. So what does this bad prime do? This bad prime need to be you can kind of fill in this example, right? So let's say if s1 prime not equal to 3, then let's say s1 prime equal to 2 here. Then you will have 1 over 3 and 2 over 3, then this thing break, right? So what's the base prime here? The base prime here is 2. Okay? Q equal to 2 in this base example. And you can kind of easier convince yourself that if something bad happens, then you must have this bad prime that is co-prime to basically everything. Okay? So you need to have this bad prime Q such that Q is a factor of S1 prime. So this notation, actually we use this once before, but anyway, this notation means divides. Okay. So also means Q is a factor of S1 prime, and so Q also divides S2 prime, and Q also need to divide R. Okay. So if Q is dividing all those three, then when you look at those S1, I should really use blue here. So if Q is a factor of everything here, then Q is going to be taken out in all those things, and you are not going to see Q, and that will cause you trouble. And so I'm saying that this is insufficient, and but you can convince yourself that this is also necessary, by being a little lazy in your proof. Okay. So if bad thing happen, there must be one of those bad Q. Also, a little digression. So this notation means divides, and we also have this notation. So let's use. Okay, it's okay. So let's say Q is not divide some S3. Okay. So if we write this thing, that means that Q does not divide S3. So Q is not a factor of S3. Okay. And okay, so that's a digression. Come back to our proof. Okay. So this bad Q exists. Okay, so what's the probability that this thing actually happen? So the probability that happen when so if we condition, we look at some Q, and so let's say, okay, so this is a little confusing. Let's say this is already happened. So we are looking through all the prime factor of R. Okay? So condition this already happened. Then what's the probability that Q is a factor of S1 prime and Q is also a factor of S2 prime? Well, S1 prime and S2 prime are chosen uniformly and independently. Okay, so here we are only say they are independent. So S1 prime and S2 prime are independent. So let's say this probability times this probability. Okay, so this is basically independence. But what's the probability that each of these happen? Well, S1 and S2 prime are chosen uniformly, and so we're thinking about what's like S1 prime mod Q, right? And Q doesn't even matter what is prime or not. But if you think about S1 prime mod Q and S1 is chosen, S1 prime chosen uniformly, then there are Q possibility, and if one is mod equal to 0, then the probability is 1 over Q. Okay? And similarly, this probability is also 1 over Q, so you just have 1 over Q squared. Okay? And yeah. So let's have a red here. So this is given prime. Sorry, given Q dividing R. Okay. And but that's just one Q. So what? But we want to upper bound probability, so we look through every Q. And we don't really know how many prime factor R has, so we do a very crude bound. That is, we just look through every prime. Okay. Obviously, if you look through every prime, that will go through every prime factor of R. Okay. So we just do a union bound of this thing happen through every Q, and that's summation over every Q over Q squared. And then we give even worse approximation. Instead of summing over prime, we sum over through every integer. Okay, so sum Q from 2 to infinity. Oh, sorry, it's not every integer. In every integer is ever 1, because if 1 over 1 squared, then we are very bad. Anyways, we really only want the constant probability, so we are doing very bad estimation here. So because prime start from 2, so we can sum Q from 2 to infinity 1 over Q squared. And then the last step you can show in homework. Basically doing the integration trick once again, and show that this is less than 3 over 4. Okay, and this is a very crude bound, but the point is that the probability that you succeed is bigger than a constant. It doesn't scale with L. It's a constant. More like it doesn't scale with R. Okay, and R scale with L. Okay, question? If not, then okay, we still have time to finish Schur's algorithm. Okay, and so that basically finished the order finding, right? So we've shown how to do order finding. Let's go through once again to our beautiful algorithm. So algorithm is we do phase estimation on this UX and 1, and we'll get S over R, and then we need to clean up S over R with continual fraction, and we will draw this in pairs, and do the least common multiplier, and you have a good probability to be good. Okay, that's order finding, and we have about 10 minutes. Can we do this? Probably. Anyway, then let's actually do factoring. So with order finding, how do we do factoring? This is totally classical number theory calculation now. Okay, and it's a bit complicated. So want to do factoring. So now big N is going to be the number we want to factor. Okay, so we want to factor it. So it's actually probably not prime. But anyway, so first you pick some x co-prime to n, because you want x co-prime to n. Well, if you fail this, then you probably succeeded at factoring, because you pick x not equal to 1. And if it's not co-prime to n, then you find some factor of n, then you factor n. Yeah. So this is probably easy. Then then here we do order finding. Now this is quantum 1, right? We spend a lot of time saying that. How do we do this in quantum? Okay. So we do order finding, then we find r such that the smallest r such that x to the r equal to 1 modern. Okay. Now there are different cases. So if r is a odd number, then this is just bad for us. Then you will just need to pick another x and start everything over again. Okay. And but if r is an even number, then you can compute r divided by 2, obviously. And then you can compute r over 2. X to the r over 2 modern. Yeah. And so here this was giving over details of this happen about probability 1 over 2 about probability over 2, although it's really sketchy. But anyway, so this should happen with constant probability, so you just keep trying and you can get this with good number of tries. And so the I guess more interesting number 3 part is now we have this x to the r over 2, and we know x to the r over 2 squared equal to 1 modern, just because that's x to the r. And then we can move things around and do this middle school factorization, right? So if we move this 1 around, then this is x in x squared minus 1 equal to x plus 1 and x minus 1. Okay. So we see that this x to the r over 2 minus 1 times x to the r over 2 plus 1 is equal to 0 modern. So this is well, this modern. So this is multiple of n. Okay. And okay. So what does this mean? We can do this not very rigorous analysis of the situation. So let's say n just has 2 prime factor p and q. Okay. This is most of the time when you try to factor n, this is going to happen. And anyway, so n equal to pq, and we know those two things is going to be equal to 0 modern. That means this thing is something like n, right? And in particular, that means how should I say? You can look at those two parts, and they should cover this p factor and the q factor. Okay. So you think about this part modern and this part modern. There are 4 possibilities. Either so if this modern and this modern. So there are 4 possibilities. So maybe this part get 4pq. So basically equal to 0 modern. And this part don't get anything, is 1. Or pq are both here. So this one part equal to 1 modern and this part equal to 0 modern. And or this one get p, this one get q, or this one get q, this one get p. Okay, so those are the 4 possibilities. And so what happened when either of them happen? So this one actually cannot happen, this possibility. And that's because of the definition of R. Okay. That's why the smallest thing is important. So remember that with so PQ actually equal to 0, okay, because everything is modern. Okay, and so if x to the r over 2 minus 1 equal to 0 modern equal to 0, then that means x to the r over 2 equal to 1 modern. But we know r is the order of I is the order of x. So I is the smallest number. So this is where the smallest being important. I is the smallest number such that x are equal to 1. But r over 2 is obviously smaller than r. So how is x for r over 2 also equal to 1? So you cannot have a smaller order than r. So this is not possible. Okay. Okay. X for r small is such that x for r equal to 1. Okay. So this is not possible. And what about this one? Well, this one we are just unlucky. So this one is unlucky, and if this happens, then you need to draw another x, just like before. Okay. And so here is another thing we brush over, but we claim that this will happen with constant probability. So if you just draw constant number of times, you can avoid this happening. Okay. And okay, now finally the happy part. So if either of these happen, then we get our factoring. So why? Because either of these happen, then well, then basically they are factors. Okay, should be fine. Anyway, so if we look at this thing, then this modern is so obviously we can calculate this thing, and this modern is not equal to okay, I'm confusing myself. So this modern is equal to p. So basically, that's not true. Yeah, I think it's easier than so. So basically, you only need to calculate this modern, then you are going to get either p or q. Okay, and we know p and q is a non-trivial factor of n, so we win. And here we have a slightly more. Okay, I think that's not very okay. So I say you can just do the reminder, but there are some other issue because you can have other factors. So what you actually need to do is yeah, so if you only do, so because it is a rough sketch, so if you only do like a division and get a reminder, you might actually get like 2p here, like 3q here, and 2p is actually not a factor of n. Okay, you can get other factors here, and I believe. And so what's the correct way to do this is you run Euler's algorithm, and you take the greatest common divider between x to the r over 2 minus 1, and then and that will give you a factor, this factor p here. Okay, and we have 1 minute. So okay, we can go over through this. So 1 minute, and this is another theorem we will not prove, but I will state over. And this theorem is about this part being constant probability. And it says that if you have some bigger number and you write it all in its prime decomposition, so you have p1, p2, pn, those are primes, and to some power alpha 1, alpha 2 to alpha n. And now if n is a odd number, and you have more than one factor, so m is bigger than 2, greater or equal to 2, then the probability that basically this x is good. So then if you draw random x, then the probability that your order is even and order is even, so this doesn't happen, and also this doesn't happen, and that's bigger than some constant. And I believe the constant, if you calculate it out, it should be this 1/2 times 1 minus 1/2 to the n. So this 1/2 is for even, and this 1/2 to the n is for this part, and that's bigger than 3/8. And I think this is slightly different than what's stated on the book. Anyway, if you want to see a calculation, appendix of the book have a pretty detailed calculation, and all we really need to hear is that this is a constant. Okay. Yeah. And yeah, as we say, x is uniformly driven from 1 to n minus 1. So things that copine to n. Uniform drawn here, and also check that it's copine to n. Okay. Okay. We're a little over time. So any question? Otherwise, next class, well, first we'll finish the detailed factoring algorithm, but it's basically just the things we have been said, be talking about in a detailed form. And I might, depend on how I feel. I might go over factoring in another form. The original short form that's not quite using phase estimation. Looks more like Simon's algorithm. Or we might go over assay, depends. Okay. Anyway, any question? Otherwise, I'll stop here. Okay, let's stop. Okay.